but now you do that systematically with power counting. And the power counting is really at the heart of this EFT with short-range interactions, all right? So that's very process dependent. You might complain about that, but that's how physics is, all right? So as I said, you have to identify a separation of scales. So here your low energy scale and the high energy scale should be limited, for example, by the excitation energy of each of the cluster. Then the binding of the valence nucleons or clusters of the system you're trying to describe sets the low energy scales. The extension of the core, the size of the sphere call is introduced perturbatively. So even though we start with a point-like approximation, it's not that we keep our description in this drastic approximation, but the size of the core can be accounted for, but it goes in a perturbative way. So perturbation theory in action. And as I said, the essential ingredient is the power counting, which is the one that assures convergence and also puts reliable theoretical uncertainties. So for more details, I refer the audience to these two papers that explains the philosophy of Halo cluster EFT. This slide is just a translation with more traditional way of handling this nuclear systems in a cluster approximation. So once you do a cluster approximation, you introduce a two-body or three-body kind of potential, which is normally a Wood-Saxon with very simple parameters. But in EFT, you replace this interacting potential by contact interactions. At the leading order is just a momentum-independent contact ones, and then momentum dependence introduces the size and also all the other complications in perturbative way. To handle bound states, you solve the Schrödinger equation with this binding potential. And then from that, you extract the ANC corrected with spectroscopic factors. But on the EFT side, we just draw Feynman diagrams, as Carlos has been always mentioning. You do resummations and stuff like that, and you end up with the asymptotic normalization coefficient, all right? Regarding bound states, you also have to solve the Schrödinger equation, but now to take into account your continuum physics. And on the EFT side, we just do an analytic continuation. We do the same sort of calculation, but the kinematics is different. And then you match your EFT parameters with observables, which are the scattering length, effective range, and so on and so forth. And for electromagnetic reactions, the traditional way, you introduce the electromagnetic operators. So you start with the dipole and quadrupole and so on and so forth. And in EFT, we just use pure QED. So our QED is a simple theory from the quantum field theory side, and we just couple that the photons the same way as in normal QED with these particles as point-like particles, right? And let me say a few things about nuclear physics and astrophysics. So, of course, is also the title of this workshop, so we have to make some connections with that. And this approach is also quite nice to be used in this astrophysical process because it involves extrapolations of nuclear reactions to lower energies, as Aurora was mentioning in this morning. And let me point out some piece of physics that we can do, which is neutrino physics. And neutrino physics involves all these light nuclei reactions. And the main ones are the ones that are highlighted with red, because the neutrinos originated from these reactions is the ones that were observed here in Earth that sort of confirm that neutrino oscillates, all right? This reaction was mentioned this morning also and yesterday in Valdir's talk, but let me concentrate on this one. So even though 15% of the neutrinos goes through this reaction, as I mentioned, is a specific neutrinos which appropriate energies that we can measure here. All the other neutrinos, they are outside the range that can be measured here in Earth. So here's the importance of these two reactions. And this one, which is helium alpha, also drives the energy for these ones, and the neutrinos from this reaction is the one that was measured by Super Kamiokande to confirm the neutrino oscillations. So I'm gonna just briefly mention our studies on these two reactions, all right? Before moving on, this Halo cluster EFT has been applied to several other systems, several other reactions, all right? I'm talking here specifically for radiative capture ones, neutron lithium-7, neutron carbon 14, proton oxygen-16, and so on and so forth, and each one of them has its own interests. And some people in the audience also has been working on that. So this is just to highlight the importance of energy to be detected here, all right? I'm not gonna spend too much time because I'm not keeping track too much on time. I'm very bad on that. But anyway, I think the important thing is that the observable that we are looking for to describe well is this astrophysical S factor that Aurora was explaining this morning, which is basically the cross-section multiplied by a Coulomb exponential, right? And the reason that we also look at this neutron lithium-7 is because this is the mirror reaction to this one, which is important for neutrino detection. But as I said, this is the second reaction that I wanted to show results here. So we are looking for describing this S34. So let me rush up. And so the first one, neutron lithium-7, the structure is quite similar to proton beryllium-7, just the numbers change a little bit. But anyway, this was a nice starting point. From the spin structure is basically the same as proton beryllium-7. It has two bound states, 2 plus bound ground state with -2 MeV of binding energy that we consider in this cluster approximation is just a 5p2 plus 3p2 symmetric combination. And this 1 plus, the first excited state of lithium-8 is just the orthogonal one to the first one. And regarding scattering states, we have two spin states. Total spin 2 has a scattering length of 4 Fermi, which is largish, and the spin 1 channel should be of natural size. So in terms of scales, this should be regarded as 1 over a low energy scale, while this one is 1 over a high energy scale. So these two parameters set the separation energies, all right? And then there is a 5p3 resonance, which is very close to to the threshold, 0.2 MeV. And we look for radiative capture, E1 transition, and also this one, oops, the one with the resonance is an M1 transition. So we studied that at very low energies. We could identify the relevant parameters in this cross section, and I'm not gonna say much about that, except that we compared with potential models when we showed that potential models fails to reproduce the low energy behavior because of normalization factor, and there is an ambiguity in the potential model that is not present in the EFT calculation. And we try to constrain that, and we have a much better description of the cross-section at very low energies. And this was later confirmed at an experiment at the MSU, that our theory is the one that are more compatible with the low energy data that was later measured. But there were complaints about our formalism because lithium-7 has an excitation, a core excitation energy, which is not so large, all right? So we should, at some point, take that into account, and we did that. We introduced the core excitation in a couple channel approach, and in this couple channel approach, this was first introduced by Bira, Tom Cohen, and Boris Gelman. In this couple channel approach, of course, you extended a little bit your parameter space, but at least we have a systematic way, especially of handling the renormalization of our EFT constants, all right? And this was later applied by Lenski and Beers, and we did that for this system. And we actually did that to put our theory in a more solid ground, but for practical purposes, it didn't change much the result because oops, I'm a little bit lost here. So I didn't have, I thought I had a figure of higher energy scale. But anyway, what I was trying to say is that this core excitation energy plays basically no role at very low energies, and it starts to be seen relevant close to the 5P, 3P2 resonance, but it's still minor effects and could be handled in perturbation theory. So one of the people in the audience is here is the one who criticized our work, so that I should thank him, because that motivates us to introduce this couple channel formalism that improved the description of our systems. And but we also noticed a few problems with their approach, which they introduced the core excitation as a dimer, but they didn't look the problem with all the channels involved, especially the transition from the non-off diagonal parts of the interaction. And we saw some renormalization issues that perhaps we can put into the discussion section, but I not have time to discuss here in the detail. But anyway, what I wanted to show is that our EFT has much more control over theoretical uncertainties, so we could express the cross-section with much lower error bars and a more consistent power counting. And here I put the uncertainties at the leading order compared with Zhang and all, that they have much larger uncertainties for this specific reaction. As I said, much of the formalism of neutron lithium-7 goes into this other reaction. It's just that we have to introduce Coulomb interactions. But anyway, the formal structure is basically the same, just the scattering parameters change a little bit. And with changing scattering parameters, we have to also change the power counting. And because of the very peripheral nature of this reaction, the power counting actually becomes even more simpler in some sense, all right? Because nuclear interactions can be taken into account very perturbatively. Most of the effects are due to the Coulomb interactions. So at the leading order in this power counting, we have just the direct interaction, and the strong part just comes from the spin 2 channel in S wave. At the next leading order, the total spin 1 enters, and also the D wave in the spin channel 2 enters. And at the next leading order is where the initial state interactions start playing a role. So before it's just a small kick that you have in the nuclear part that plays a role in this reaction. And initial state interaction is a very high energy, well, higher order interaction that I should say, all right? And well, I don't have much time to say about that. What I wanted to say here is that emphasizing the peripheral nature of this reaction, all right, which is based by this approximation of the S factor at very low energies. And this is very much compared with similar expansion that Daniel Bay did for this reaction, right? We did Bayesian fits below 500 MeVs, and that's our result. Also, if you go a little bit higher in energy, we have to take into account this resonance. And that's fine, that's also incorporated in our formalism. But at very, very low energies, for extrapolation purpose, this resonance play a very minor role, all right? So I think I have to rush a little bit here. In our Bayesian fits, we also put a normalization of the cross-section as a parameter, and so different experiments have been rescaled with that. They enter as Bayesian parameters here. And once you put all the normalization factors to the same scale, the figures looks. I have a well. Let's see where I'm going. Okay, so you see some all of the experiments falling in the same trend. This is an artistic illustration because it's not that all experiments are falling agreeing with each other. It's just that they differ from the normalization of the cross section. All right, and with that we end up describing this cross section with much less parameters, and this much less parameters is due to our power counting. So at the leading order we have just let's see. I think I had a slide with that. So at the leading order, we have just one parameter. And if we include this region of the resonance, we have one more. And this is at the next leading order, the next leading order. So we have a total of 6 parameters, while the other approach, EFT approach, they need at least 7 parameters at NLO. So with this power counting, we are much more economic in terms of coupling constants, all right? That needs to be determined by experiment, and our convergence is even faster. Our S factor extrapolated at zero energy, it has this value, 20.5 plus or minus 0.7 EV times B. And this is very close to the theoretical uncertainty that people has been saying that is appropriate to constrain neutrino physics. And this also enters as in the solar fission tree. This value is the recommended value, all right? So for this other reaction, things are a little bit more complicated because the power counting is lower, has is lower convergence pattern. But anyway, we have to draw these Feynman diagrams. First, the Coulomb interactions, and also the ones that are pertain to the radiative capture. So we have sort of direct types of radiative capture diagrams, which means that basically these processes are driven by the initial state Coulomb interactions. And these diagrams of type B are the ones that include initial state interactions. And for this capture, this initial state interaction is more relevant. And even more, for renormalization issues, we have to introduce two-body currents at current at leading order. Okay, thank you. But here we also did two kinds of fit. One that goes up to 500 MeVs and one that goes up to 1,000 MeV. Here the fit is not so perfect, so they differ slightly at the leading order, getting to much more agreement at next leading order, but still data doesn't allow us to make more better description because you can see the large error bars that we have in the observables. So it would be good if we have better experiments on that, especially on the radiative capture ones. But recently people have been looking at the scattering process, and but we didn't update that with that. So this is the main message, that we have a strong correlation between two-body currents and renormalization constants. So since both enter at leading order, they are not truly independent, but we saw some correlations here. And here we compare a fit with two-body currents and no two-body currents, and with no two-body currents we see a big change in the renormalization constants, all right? So also our results became a recommended value for the S factor. And since I'm out of time, I end up here with this summary slide conclusions, just saying that we look at this radiative capture reaction in a couple channel approach, which present more convergent power counting for proton beryllium 7. And to our opinion, has a more solid theoretical ground because we don't, renormalization is quite simple and we don't enter into those issues. We have a more controlled over the theoretical error bars. And for this other reaction, convergence is not quite good. We have to introduce the two-body currents, but still we have a reasonably good description of data. We are just looking for our experimental colleagues to improve their measurements to help us to make better predictions. So thank you for your attention.
So thank you, Renato.
Proton beryllium 7, can you put back that transparency? You say you calculated it in EFT, that this is a magnetic resonance.
Yes.
Yeah, so you say you calculated it with EFT,
Yes.
but you have gyromagnetic factors there, which are medium dependent. It's not the free, so for the beryllium-7 and for the proton, you have different gyromagnetic factors, and they are medium dependent. I do not know how can you do this in effective field theory.
We just take the PDG values. That's it.
And you reproduce, because you can also reproduce it with the simple, with Saxon, and you do the
Yes,
magnetic
and
background.
that's yeah, also we did that. I think this figure is a wood Saxon type of thing.
But then it's not EFT
No, we did that with both. All right,
with both.
with both,
Okay.
and we compared and we checked that they are equivalent. So
Okay, good, excellent.
mhm.
Daniel?
Thanks, Renato. So I think I like the more careful organization of the contributions at low energy that you all did, right? And I think that, as you say, in the end, that's more efficient. I do want to comment that because, like you all, we did a Bayesian analysis of the parameter space, we could see that the effective number of parameters was lower. And so I'm going to put in a plug, which I don't think you will disagree with, for Bayesian analysis of your EFT, because you can then sort of post facto see how many actual parameters you have. Right, so we could see that certain parameters were filling out their prior, certain parameters were degenerate, et cetera, right? So I don't know. So that's essentially a comment. The question I was going to ask you, if you wanted to comment on the alteration in the theoretical uncertainties of these important reactions for solar fusion as the result of EFT folks getting involved and computing them in order-by-order expansions. So in other words, how did the theoretical uncertainties for beryllium-7p gamma and helium-3 alpha gamma change between solar fusion 2, when everything was done in potential models for these reactions, and solar fusion 3, when essentially the standard became EFT? Do you want to comment on the change in the theoretical uncertainties between those two evaluations?
I have to confess that I'm not aware of Solar 2 results, all right? So I cannot comment much about that. But I mean, I'm biased to say that EFT is nicer because you have much more control of the theoretical uncertainties. Rather, when you do a potential model, as I said in the neutron lithium-7 case, maybe you have extra parameters that you are adding up in your potential model that doesn't necessarily are the best ones. And probably they are correlated and should be reduced. In EFT, you can do that. So you have much more control of the theoretical uncertainties due to that. And I think that's what I can comment on that. And that's what allows us to reduce the theoretical uncertainties, right?
Can you do a Bayesian analysis to geometrize this boat in a way that it becomes a parachute? It will never happen. So, no, it's a comment, is that if you have a model and you do a Bayesian analysis, but the model is not, you are not going to transform the boat into a parachute, no matter what the parameters of the boat that you want to change. So,
No one claimed that, right?
So, but I think this is actually exactly Renato's point, and I think the paper he wrote with Gautam, the PRL in 2011, is a great example of this, is that the thing about EFT is that it spans the space of all possible rescue mechanisms up to the accuracy to which you want to work. And as an inventor of Halo EFT, I imagine that you support this statement.
Thank you, Daniel. That's what I was going to say.
Any other questions? Maybe I have a last one. Can you go back to your comparison of the different calculations for the lithium-7 reaction? Yes, so this plot
this
that
one.
you just had.
Okay, all right.
So which is which here? If I
Oh,
is there a discrepancy between the two different EFT frameworks for this reaction?
yeah, this one is from Shili Zhang and Daniel Phillips. All right. Sorry. And Ken All. Yeah. Sorry. And the discrepancy is on their side. So on our side, we are here. All right. So I don't see a discrepancy from my side.
Yes, so I was at a discrepancy between the two EFT calculations, right? And I mean, assuming they both followed EFT procedures, you should agree within error bars, right? The upper plot.
So what, like, are these fit error bars or are these higher order error bars? Because, like, I think this is Hans's question, right? It's like, do these agree within the higher order uncertainties?
Yes. Yeah, this I think is leading order, and this is next leading order. I'm not sure if that's correct.
Yeah, as I recall, the leading order to next to leading order shift in the system is fairly large, right? So which is what you're showing here, right?
In your case, yes. In our case, we fit that to the thermal ratio, I guess. There were two parameters.
I think ours was a prediction, right? We predicted the thermal cross-section based on input ANCs from Ken's ab initio calculation.
Yes, we did it the other way around.
Yeah, you did the other. So you fit these data, and for us, this is a prediction.
Ours is a post-diction, I would say.
But you said you fit the thermal cross-section, right? Which is this, the top left panel.
Yeah, I think was.
But we did not fit the cross-section. We predicted the cross-section based on the ANCs from a 7-body, from a 8-body calculation.
Yes, we fit that, and we got the ANCs and compare with yours, and it's compatible. So I think that's.
Okay, so I think that is cleared up now. I don't see any other questions, so let's go to the coffee break, and we'll continue at 10 minutes to 11, right? Okay. Let's thank Renato again.